Hi, I'm Mr. Taru. Hopefully you just watched my video where I did a lecture on comparing two means. And I finished the video with examples of doing a two-sample mean t-test and a two-sample mean confidence interval. Well, now we're going to do proportions. And through these notes, and then ultimately ending in a couple of examples, the biggest difference, besides of course we're using different formulas for standard deviation and mean, is that the only time in Intro to Statistics that you do a t-test is when you're working with means and you have or only have at your disposal the sample standard deviation. Now with proportions, we're going back to doing or using the z distribution, the normal distribution. So remember, all of this video is going to be involving z-scores, z-test, z-intervals, because the z distribution, that standard normal distribution, because we're working with proportions. We're not using means and the sample's standard deviation. Even though you'll hear me say standard error, it will not be standard error of the mean, it will be standard error of the proportion, and again, z-scores with proportions. So, to start off, we are combining means, whether it's we can combine means and variance, whether it is addition or subtraction. However, as you write these notes down, remember that this is going to be a comparison between two proportions. And we do comparisons with subtraction. How heavy am I compared to somebody else? Well, I'll subtract those two weights and go, well, I weigh more or less by a certain number of pounds. So we do comparisons with subtraction. I'm just writing the plus or minus here because you can add means, and thus, it's there as a possibility. But for comparisons, we're doing subtraction. So, the mean of x plus y is equal to the mean of x plus or minus the mean of y. So, the mean of p hat plus or minus p hat sub 1 plus or minus p hat sub 2 is equal to the mean of p hat sub 1 plus or minus the mean of p hat of p sub 2. P hat means sample proportion. Capital P with no hat on it is the population proportion. Now, this rule for combining means is not dependent or does not require the two samples to be independent. So thus, there's not that condition there. And you can add or subtract means, but again, for the comparison purposes, we will be just doing subtraction. Since the mu of p hat equals p, since the center of our sampling distribution is the same as the population distribution, then we can say that the mu of p hat sub 1 minus p hat sub 2 is equal to p sub 1 minus p sub 2 as well. Standard deviation. Well, I'm saying standard deviation, but that's really, now that I'm looking at it, what I'm finalizing down here in my notes. This says the variance of p hat sub 1 minus p hat sub 2 is equal to, and I'm running through the formula for combining variances, and I should have wrote that generic formula up here. If you want to add two groups together, you need to combine the variances. Now, whether you're adding those two groups together or subtracting, we only ever add the variances, and variance is standard deviation squared. So I'm taking the standard deviation of a sample of a proportion, squaring it, plus, and that'll be the variance of the first sample, plus the square root, or excuse me, the standard deviation for, again, a proportion, that's the square root of p times 1 minus p over n, the sub 2's because it's the second group, and I'm squaring that standard deviation to, once again, make that a variance. So thus, standard deviation squared, or variance, of the first group plus the variance of the second group equals p sub 1 times 1 minus p sub 1 over n sub 1 plus p sub 2 times 1 minus p sub 2 over n sub 2. Now, if I'm adding the variance from the first group with the variance from the second group, well, that's great. We add variances when the two groups are independent. My textbook only uses the combination rule for independence. There is a different way of combining variances when they are dependent that will not be discussed in this video or in this class that I'm teaching, Intro to Statistics. So I need to square root this combined variance to get the standard deviation of p sub 1, p hat sub 1, minus p hat sub 2 equals the square root and I guess, do I need to really say it again? This formula that I'm pointing to is going to be on your formula sheet for the AP exam. So you're not going to have to memorize it. You're just going to have to know, where it came from and what it's used for. I'm showing the steps of where the equation came from to remind you basically of an old concept. How do you combine standard deviations? Well, you don't. You add variances. And by the way, you do never subtract them. You only add variances, regardless of whether you're adding the two groups together, maybe finding some kind of combined value, or you're subtracting. Let's continue this lesson on to some formulas. Now I'm going to give you another standard error formula. Remember that confidence intervals estimate their only purpose of a confidence interval is to estimate the population parameter. So if you are setting up a confidence interval, you are trying to estimate the actual value of p, the population proportion. So you cannot use it in the formula for standard deviation. The last screen that I had there looked exactly the same, except for these p-hats were missing, and p's, just p alone was in its place. Again, p-hat, sample proportion, no hat, population proportion. So when you are using the samples, proportions of success, probabilities of success, you're going to call that the standard error of the difference of those proportions. So the standard error of p-hats of 1 minus p-hats of 2 is equal to, and this is the same formula from the other screen, only with the hats added in. Now why the difference? When you do a significance test, now that we've learned how to set up our hypothesis statements, our null and alternative hypothesis, let's not forget that when you set up a null hypothesis, that is something that we are assuming to be true about the entire population. We're looking for evidence against H sub O, and thus we may possibly, if the p-value is small enough, reject it. But we are initially starting off assuming that H sub O statement is true. So we're assuming that we know the population proportion. Well, again, confidence intervals estimate the population proportion. So thus, you cannot use an assumed to be true value in a confidence interval. The idea of a confidence interval is you don't know anything about the population, you collect data, you create a sampling the confidence interval from that sample's result, and from there you estimate or set up an interval with some level of confidence to try and capture the true population parameter. So let's not forget confidence intervals, p-hats. We got a formula for a z-score. Again, proportions, z's. If you're working with means and you're using S of x, that's a t-distribution. None here. Estimate minus parameter over standard deviation of the estimate. In words is what you'll find on the formula sheet. You'll have to just find the standard deviation formula somewhere on the formula sheet and know that you need to plug it in. Confidence intervals are estimate plus or minus critical value times the standard deviation, or excuse me, in this case, standard error of that estimate. And let's not also forget that what comes after the plus or minus is our margin of error. Now, I forgot to mention this in my video. When I first introduced confidence intervals, I've gone back and added in a little bit of text, like a bubble over the video. The purpose of a margin of error is to give you a cushion solely based on the randomness of just random events. When you flip a coin 10 times, you're not going to get heads 5 times and tails 5 times. You're going to get around that value. So that randomness in our numbers is what the margin, sorry, words escape me there. The margin of error takes care of that randomness in our sample, or in just, the random phenomena that we're looking at. It does not account for such things as non-response, undercoverage, a biased or poorly designed sample. It does not account for any of that. That's your job as a statistician, setting up a good sample or sampling technique. Margin of error just takes care of randomness in our values. Conditions, same rule of thumb as I've said now for many, many chapters in a row. SRS, normality, and independence. SRS, each sample needs to be from each sample needs to be an SRS from their own population. Normality, Remember the rules for the binomial setting, binomial counts, binomial settings? Let's see, binomial setting has 4 checks, 2 outcomes, set number of observations, constant probability, and independence. Normality check for the binomial setting is n times p and n times 1 minus p both must be greater than or equal to 10. Well, in 2 sample tests are more robust. So each of these multiplications, n sub 1 times p sub 1, n sub 1 times 1 minus p sub 1, and the same formula for the second sample, those now only need to be at least 5. It kind of makes sense, right? It's sort of like you're taking those 2 samples and combining them, and 5 and 5 is 10, which still matches up with the old rule that we had. And independence. Your 2 samples need to be independent. The result of one sample cannot influence the other. And within each population, if you're sampling without replacement, the population must be 10 times larger than the sample size for each of the population that you're doing an SRS from. Got a few more notes before we start our example, so here we go. I lied. We do have an example. There are some more notes, but I want to do an example about confidence intervals and then give you a few more notes before we move into the 2 sample proportion z-test, because we have some kind of an issue that we need to talk about before we do that example. So we're going to do a 2 sample proportion z confidence interval. You take an SRS of 380 men and an SRS of 370 women to learn if there is a difference in snacking habits. Well, you learn that 60.8% of the men and 53% of the women say that they snack, through the day between meals. Estimate the difference in snack rates with a 95% level of confidence. Now, I'm going to do this pretty much this exact same question in the second example, but when we set up our hypothesis statement for two sample proportion z-tests, we have an issue with H sub O, which causes us to do a slightly different process. So let's look at this data and let's estimate the difference. Well, your conditions. An SRS for each group is stated. Normality. N times P and N times 1 minus P must be greater than or equal to 5 for each of the 2 groups. So I've got my numbers in here, and I'm not going to read this out to you, but all of these numerical values are larger than 5, so we are going to pass the normality test. And independence. Each population is greater than 10 times the sample size. Now, if it was an experiment, and you just have a collection of subjects or units, and you randomly assign them to 2 treatments, that is enough for independence. When you're sampling, though, you definitely need to make sure that your populations are over 10 times the sample size if you are pulling from that population without replacement. So there's our conditions. And please note that I've also stated what I'm doing. When you do these problems on the AP test, and you're at the full-blown, a very simple problem, setting given, and then just, state the difference. They may or may not say use inference toolbox, but if they just give you a very basic, here's a setting, tell us something about it, you need to make sure that you tell them what you're about to do. 2 sample proportion z interval. Then do your checks, and now here we go. Estimate plus or minus critical value times standard error of the estimate, since we're doing a confidence interval, and its purpose is to estimate the population proportion. So we observed some p-hat values, our sample proportions of 0.608 minus 0.53, plus or minus our critical value. Again, let's just stress over and over again that we do not do t-scores here. With proportions, it's always z-scores. So look up that 95% level of confidence, most convenient places on the bottom of your t-table chart, and then just go to that bottom line where it says infinity or z, and your z-star value will be 1.96 times the standard error between our 2 sample proportions. So p hat sub 1 times 1 minus p hat sub 1 over n sub 1 plus p hat sub 2 times 1 minus p hat sub 2 over n sub 2. And when you get that typed into your calculator properly, do one for plus and one for minus, then you'll say I am 95% confident the difference in the percent of men and women who snack, obviously in between meals, is somewhere between 0.75% and 14.9%. And I am doing all this with all the hand calculations, using the charts. I will be very soon be using or creating videos to help you see or understand how to use your TI Inspire or TID, probably just your TI Inspire to help set up these intervals and these tests. I do believe that using the formulas, doing these calculations by hand, using the tables helps, in my opinion, to build the understanding better for students. Also, when you take these big tests, they are looking for any opportunity to give you some extra credit. And the more work you show them, the more opportunity maybe, especially if it's just a small, tiny mistake, for you to get some extra, some partial credit back. If you just type this into your calculator, spit out an interval and write it down, especially if you just typed in a number wrong and everything else was right, they're not going to have that work to look at to possibly give you some partial credit. So that's just my opinion. Let's take a look at now a few more notes before we do the two-sample proportion z-test. Bam! Two-sample proportion z-test. When we set up h sub o as no effect, our treatment in an experiment has no effect, or no difference, I'm not expecting there to be any difference between these two samples, we are assuming the two population proportions are equal, and thus our h sub o and not to h sub a yet. Our h sub o statements are going to be p1 equals p2, or, as I prefer to set it up, h sub o is p1 minus p2 is equal to 0. I prefer this design on my hypothesis statements because if I think about how I'm going to do my subtraction before I start the problem, then I'm going to determine how I'm going to shade before I start doing the work, and I'll make sure that that's very, very clear, just to make sure when I'm done I don't end up shading the wrong side of the bell curve. Now, I seem to remember my older textbooks occasionally given a two-sample test, whether it was means or proportions, where, the expected difference was not 0. But my current book, it seems like every single question we ever do, and it is much more common, even in the older books that I had, where, again, we assume these to be equal, and thus the difference is going to be 0. Now, in that setting, when P1 is equal to P2, and we're assuming it to be true in H sub O, and we're going to look for evidence against H sub O with our significance test, we are going to set up a pooled proportion. Now, with a two-sample mean t-test, I told you to never, ever, as far as my suggestion goes, and again, this is only intro to statistics, I'm not a master of, any upper levels of statistics, to avoid doing the pooled two-sample t-test, because we must assume that the variances between the two groups are identical, and thus that's almost never going to happen, so just do the regular two-sample mean t-test. But this statement of H sub O is that P1 equals P2, this is a very, very common H sub O statement, and thus you are going to be doing a pooled proportion z-test, a two-sample pooled proportion z-test, quite often. So, to find our pooled proportion, and again, this is only when you're going to have H sub O set up as P1 equals P2, or they subtract to be 0, is P hat of the pooled proportion, that's what C stands for, combined, is the combined successes of counts divided by the combined number of trials. So x sub 1 plus x sub 2, that's the number of successes observed in each one of your trials, over n1, n sub 1 plus n sub 2. And thus our standard error, again we're doing standard error because we're using our pooled observed sample proportions in this calculation. The standard error of p hat sub 1 minus p hat sub 2 is equal to the square root of p hat pooled, or the pooled proportion, times 1 minus the pooled proportion, times 1 over n sub 1 plus 1 over n sub 2. This is a different standard deviation formula that I just gave you at the beginning of this video, where you are doing a true two-sample proportion test. And again, we do that when we are not assuming that P1 equals P2. Even though my book seems to do this almost all the time. So when H sub O is equal to P1, or when your H sub O statement is P1 equals P2, this is what your z-score formula is going to look like. Again, only z-scores with proportions. And again, my speech or my sales pitch on how I like to set up H sub A, my calculator and your computers will use these inequality statements in their menus, but if as I teach it, if you determine how you're going to set up your subtraction ahead of time, and you, of course, got to stay consistent with that, then you can go, well, I'm expecting something, and based on my assumptions before I collect my data, based on my alternate hypothesis statement, I'm expecting a positive difference, so I'll shade to the right no matter what the numbers reflect. Or if I have my subtraction set up and I'm expecting a negative difference, I'll make sure to shade to the left. And in a not equal to setting, a two-sample test, of course, we're going to shade both tails. We'll only find one of them, of course. You can't have a statistics that's higher and lower than the mean at the same time, but you'll find that one z-score. You'll find the tail area, whether it's the lower tail and you keep the z negative, or whether you do take the absolute value of it and find the upper tail. I don't care. Find an area of the tail and double it. I feel that these settings make it clear what direction you'll shade when the problem is done, and thus make sure that you don't accidentally shade the wrong side of the bell curve when you come up with your p-value and try and draw your conclusion at the end of the test. So, there's my intro in the design of the two-sample pooled proportion z-test. Let's see what it looks like in practice. Bam! Alrighty then, let's do this example and call this a day. Do men or women snack more? Well, again, you survey 380 men, 370 women. We again have an SRS, same results as the previous example when we did our confidence interval. Is there convincing evidence that there is a difference in the snacking habits between genders at the 5% level of significance? This question is not worded with the assumption that men or women are going to snack more than the other. It's just, is there a difference? And that language is going to set up a two-sided test. I'll adjust it to be one-sided when I'm done with this example. So, again, is this means or is this proportions? If it was the amount of snacks in a day, then it could very easily and actually would be a two-sample mean t-test. But the response to each trial, each observation is, do you snack? Yes or no? So we need more than that for the binomial setting, but that is a huge push in the right direction to say this is going to be a proportions. Is there a set number of observations? Is there two outcomes? Is there a constant probability? Is there independence? And basically this is yes. But especially hone in on every trial, every observation has two outcomes, so this is probably going to be a proportions test. We could also do it as a binomial count as well, but we're going to stick with proportions. So this is going to be a pooled two-proportion z-test. Now again, the reason why it's going to be pooled is because we're going to assume, is there a difference? Well, where does the difference start? If we take their snacking, if we take their results and subtract them and get an answer of 0, then there is no difference. But anything other than 0, right off of 0, means that there is going to be some sort of difference. And so thus, H sub O is that the proportion of men is equal to the proportion of women who say yes, or you set it up with subtraction and have it equal 0 like I prefer. Define your variables, and H sub A, again, because of this word right here, is going to be a two-sided test. The proportion of men is not equal to the proportion of women who say yes, or the proportion of men minus the proportion of women who say yes is not equal to 0. I did say not equal here, didn't I? Okay, so I've stated what I'm going to do. I have stated my hypothesis. I have defined my variables. I'm now going to, because I've recognized that this is a pooled proportion because of the way H sub O is set up, I'm finding my pooled proportion, my p hat sub c, combined proportion. All my successes. Now where did the 231 and the 196 come from? They could have been given in the problem that I didn't want to write all because, well, of course I made it up off the top of my head. Well, not exactly, but I did make it up. It took a little bit of work. But it could be, the number of successes could be given to you, or, 60.8% times 380 and round off to the whole number count. 53% of 370 and get that whole number count rounded off. And you get 231 plus 196. My success is based off of my probability of success over 380 plus 370, my number of, the number of trials for each sample, and we get a combined pooled proportion of 0.57. Okay, now we're ready to do the conditions, and then finally do a calculation and draw a conclusion. So again, our conditions. Our SRS is stated for each group. Independence, the population for each, men and women, should easily be larger than 10 times the sample size. I'm pretty confident there's more than 3,800 men and 3,700 women in our entire population. Now, normality. I've shown the work again, n sub 1 times, p hat, the combined proportion, n sub 1 times the 1 minus your pooled proportion, n sub 2 times your pooled proportion, and n sub 2 times 1 minus your pooled proportion. Kind of the same old n times p, and n times 1 minus p is greater than or equal to 10. Now, if it's a two-sample test, and those two samples are independent, we're not assuming that the proportions are equal, then the check was each of those need to be greater than or equal to 5. With a pooled proportion, my textbook says as a conservative value, make sure that all these are larger than or equal to 10. If these values are between 5 and 10, as far as my textbook reads, it's sort of like, your interpretation, how comfortable are you with the normality of the data. Just, think about that normality, maybe mention that there could be an issue, and which could put a little bit of doubt into your normal approximation. But, so they say 5 is there, but 10 is more conservative. They're easily all over 10. So I've done my statement, I've done my hypothesis, I've defined my variable and done my pooled proportion. I've done my checks now. So finally, I can set up my z-score work, estimate minus parameter over standard deviation or standard, error of the estimate, the coming from the pooled proportion. We get a z-score value of 2.16, so we are 2.16 standard deviations above the mean of 0. Our p-value is 2 times 0.0154. Now, if you're using a chart to do these problems and doing it by hand, you'll find the area of one tail and you'll double it. If you're using a calculator or computer to help you out, it'll tell you, roughly that this p-value is going to be 0.03. I've, of course, rounded it off. So if you tell a calculator or computer to do a two-sample or a two-sided test for you, it will give you the area of both tails together. Don't multiply it by 2. The observed difference of 0.07 or 7.8%, or one that's more extreme, just giving you the exact definition of p-value, has a probability of 3%. This is less than the level of significance of 5% stated in the problem, and thus we reject H sub O. We reject that the snacking habits are going to be the same. Make sure, especially if you're going to use my tip on setting up H sub O and H sub A, make sure that you do the subtraction in the same order when you get to do your z-score, or in case you're working with means, your t-scores. You don't want to decide how you're going to do your subtraction, decide how you're going to shade, and then get your subtraction screwed up in your work, because you will get a little bit of a wrong answer there. Now, before we're done, what if this said, well, I don't want to erase this, it will take too long, but what if it said, is there evidence that men snack more? So let's just change this for a minute. Instead of this statement, I said, is there evidence that men snack more than women? For some reason I felt like that was a possibility before I collected the data. If it was, what's a probability that men snack more than women, then more still starts at 0. Even if the men's proportion is just a tiny bit higher, that positive difference starts, at 0.000001 or whatever, something like that. So my H sub O statement is not going to stay the same. But if I'm expecting more yeses from men than women, then this is going to become, let's see, large number minus a small number means that I have expecting a positive difference. So if I'm expecting more men to snack than women, then that now becomes a one-sided test. My p-value is going to stay 0.0154 because I'm not going to double it. And just because I didn't do a bell curve drawing for the last problem, let's do one here. I'm running out of room. We got a bell curve centered around 0. We observed a difference of 0.078. And I'm expecting a positive difference. If I make sure that my subtractions stay in that same order, I should be expecting a positive difference, and this inequality tells me what direction to shade. I'm going to shade to the right. So this upper tail area of 0.0154 comes from that upper tail. Again, I like this alternative hypothesis statement better because it'll remind me of how to shade when I get done with my problem. I'm Mr. True. Bam! That's two sample proportions. Go do your homework.